Okay, so welcome everybody. Today is Wednesday, February 5th, 2025. This is the first PICUP webinar of the year, and I'm excited to see all our attendees. I want to be respectful of personal choices, but if anything, I would encourage you to enable your camera so that our invited speaker can see your face and your reaction to the presentation that he is delivering, of course, as long as your internet connection allows for the video connection. Okay, so once again, it will be very nice if we can see your face. So today I want to introduce Mohammad Soltania Ha from Boston University. Mohammed is highly active in service at APS, and he's also a leader in the data science group. Um, Probably with that, I will let Mohammed give his talk.
Thank you, Patricia, and thanks everyone for coming to this webinar. Thank you for inviting me. Let me share my screen, bring up my slides. Okay, so I want to first maybe ask if people are not speaking, they could put their microphone on mute. That would be great. There's some background noise. Thank you. All right. Hello again, and let's get started. I will be talking about integrating data science and AI into undergraduate physics curriculum. I would like to talk about this project, DSE Cup, that I have been involved in the past few years with. It's a collective work and get also some feedback and have some discussion. So I don't want it to be entirely just me talking to my screen in this case, but would love to hear your feedback, your thoughts, your potential involvement with this project in the future. Also, I should say that I'm affiliated with Boston University Information Systems Department, which is housed within the business school. I'm a professor there, but I'm also affiliated with Google Cloud, and I have a service role there as a faculty expert. And none of the things I talk about here are representing any of these institutions that I'm affiliated with. My personal opinion, except I would be representing the DSE Cup project, and I am speaking on behalf of the group and presenting some of the work, amazing work that PhD students and postdocs that we've had worked on in this talk. Just a little bit about my background, so you know who I am. I did my PhD in computational physics. And after my PhD, I joined a company as a data scientist before joining Boston University to teach data science. When it comes to the American Physical Society, as Patricia mentioned, I been involved with the data science group. I was the founding chair. I co-founded the group in 2018, and I've stayed involved. After my tenure was over, I helped the PIs who applied for the Innovation Fund at the APS and formed the group of DSE Cup, which is the Data Science Community of Practice. And so I was the editor in chief for that society. Right now, I put an end date here for this because our funding finished and we haven't applied for a new round. But there's a chance that this will continue. I hope it does. I'm also a brand new board member of APS. Started my term just very recently, this month, last month. And I teach data science, data analytics, business analytics, different variations at the master's level at BU. When it comes to research, I've been involved in different types of data science research, either most recently LLMs, but also time series forecasting and computer vision, um, outside of the physics research. So what is relevant to this to this talk. So let me, yeah, actually, I'm getting already a question in the chat, which I think is great, and I would love to have this session to be interactive. So I'm going to take the question now, and we are going to have time at the end for questions too. So the question is, as faculty expert at Google Cloud, is a role that informs Google of what features university faculty want from Google Cloud applications or something else? So good question. This is a somewhat active position because I think a little bit in hibernation. But the idea behind the Google faculty expert, was to have a cohort of 40 of us around the world to advocate for cloud computing. Get invited. Google would send us. We started right before COVID, so it became mostly virtual. To go to conferences and talk to other faculty members who want to use Google Cloud for their classes or for research, and basically being an advocate for cloud computing when it comes to research and teaching. So that's what I've been doing. And along the way, there are many situations that they reach out and they ask for feedback. For instance, I have one of the slides coming up where we can get credits from Google to distribute to our students. They've asked me to test, to give feedback, how easy it is for my students to retrieve, things like that. So we help in that areas with the developers at Google. I've talked to people at Colab team, but that's not the main scope. The main scope is just to have some folks that can talk to other faculty members around the world and help them get started with the computation, using Google Cloud. Okay, so I hope that answers the question, but I'm happy to chat offline on this as well. The Before I get started with this talk, I first wanted to just talk about cloud computing a little bit, how I see and how it can help with the equity issue in data science. And this equity could be at a personal level, could be at a company level. And first, defining equity. This is one definition for it. Equity is the provision of personalized resources needed for all individuals to reach common goals. And the resources would vary from one person to another, from one project to another. And when it comes to data science, you can think about the inadequate hardware, ineffective software, data access, slow internet connection. Patricia just mentioned that. You can imagine how big of a block that is for people who are working with large data sets, poor infrastructure. These could block or slow down individuals or organizations. And, cloud and cloud computing can address these issues to some extent. So the yeah, so I think there's some background sound. Patricia, if you don't mind muting people who are not speaking. And let me see also if there was another question. Okay. All right. So now let's come to data science education. I talked about the previous slide because these are real issues, and when you're teaching to students in the classroom, you have to think about the compute power, right? I'm sure you all have taught some sort of computational physics or similar courses. that you have to think about, what students can achieve, and hardware is a big piece, but also software and access to material. So here in this talk today, I want to address these things and specifically focus on the material and where DSE-CUP can be helpful for uh, physics faculty members who are teaching undergraduate physics and would like to bring in some content into their physics courses that is leveraging data science and helping the students in both ways, both the students' continuation in their education, but also in the job search if they're not continuing with an advanced degree. So when it comes to hardware, you can think about laptop versus cloud. This is, thinking of cloud is where you can have a laptop with a 4 GB memory, but get access to the same or even more powerful cloud resources than the best laptop in the room, right? And so that's I've set that for myself as a requirement for all the classes I teach. And we've done something very similar for the DSE-CUP project, which is all the code that we're running will be run on the cloud. And we'll talk about that in a little bit. The benefit is everyone will have access to the same compute power. The secondary benefit here is that if the code runs in one instance, it's going to run on the same identical instance that everyone else has access to, as opposed to if it ran on my laptop, it's not guaranteed it's going to run on your laptop. And then when it comes to the software, you have the open source. You also have third party or cloud. And for the DSC Cloud project, we focus on open source when we can and when we could, and because the open source is awesome, right? It's free and everyone has access to. And so we'll talk about that, what we have based the content of our component, the different components of the project. And then when it comes to material, before getting to DSC Cup, I just wanted to give some pointers in case people who are on this call, they would like to, they're not already teaching data science in their classes, they would like to add some content. These would be good materials to start with. Uh, Jake Vanderplas is a physicist, astronomer. He has two really good books. One is a whirlwind tour of Python, and in fact, I don't think this book you can buy anymore, but there is the free PDF and comes with a accompanying GitHub. And then Python Data Science Handbook, you get access to free online version, but also you can buy. Also comes with GitHub that you can download, modify, and reuse. So for some of the content that you might want to use, maybe one of the notebooks or several notebooks from one of his books here would be, that's all you need. When it comes to machine learning and deep learning, this is my recommendation, the Francois Chollet's Deep Learning with Python book, which is written by him, who is the founder of Keras. And for one of the challenges that a lot of students face is that they come to the class is based on some sort of machine learning, data science, and they don't have any Python coding background, uh, or they don't have any programming background at all. So it's pretty tough to be able to teach them programming, coding, and also some really cool physics concept that you want to teach that involves data science, right? So it's a lot to include everything. I would suggest to use platforms such as DataCamp and give them as a pre-work before the course start. You can specify, you can say these two courses, each course, for instance, takes 4 hours. So they can work on their own. However, this platform is not free. So it goes a little bit against the open source philosophy that I would like to follow. However, you as a faculty member, you can apply for a 6 month classroom premium access for your students. And I've used them for 7 years now, and they're great. It takes a few days. You apply, it takes a few days for you to be approved, and you can specify, say, okay, if you don't know any Python, go take these 2 or 3 courses. If you already know, you can skip them, right? So that way you can also think about equity. You can bring everyone kind of to the same level before day one of the class. And then for Google Cloud Compute, Google Cloud itself, there is this resource that you should also apply for the educational credits beforehand. This I have a link here for it. I wonder there's a yeah. I would also put a link to my slides in the chat in a little bit. So, because I understand you cannot click without having the link. And there was a comment by William, who is one of my most amazing collaborators when it comes to data science and physics. We've been involved in a few different projects together. Fast AI can also be good for some students and or software carpentry. Exactly, 100%. Actually, William is one of the PIs of the PICUP, and I'm talking about. So if you had any difficult questions, I'm hoping William stay until the end. I'm passing those questions to William. All right. So software. What do we need? We need some sort of programming. The choice we made is Python because that's the choice of industry, and AI and data science. Most of the development is happening there. So that's what we went with. Coding environment, we chose Jupyter Notebook because it's just so intuitive for everyone. Also, it's very, very nice. You can bring in the physics concept and coding everything in one place. For a platform to run, we chose Colab, and I'll talk very briefly on Colab. I would love to know how many people have used in the past. I don't know if it's what's the easiest way to collect that information, but I will give a very brief intro just in case there are some people who haven't used it in the past. But this is basically an excess capacity compute of Google sitting in the cloud that when they don't need it, they allow us to run our Python code on it for free. And it's wonderful because everything is pre-installed and all the students will have access to the same exact hardware, which is a pretty decent hardware, the free version. I've never had any. And for version control, GitHub. So that's also what we're using for the SE Cup. Now, when it comes to the open source libraries for data processing, we focus on NumPy and Pandas, which are pretty standard. For visualization, Matplotlib and Seaborn. For machine learning, scikit-learn, TensorFlow, Keras, PyTorch. So we switch between these libraries. And, we didn't have a situation where we use BigQuery, but you might end up working on a project. Either it's, setting up your students to work on a research project, or for a course that you have a lot of data and need a big data warehouse. BigQuery is a fantastic solution on Google Cloud that can handle not only terabytes but also petabytes of data with no problem. Okay, so now again, I think this is the last couple of slides before I get to the actual project. The just again, just making sure everyone's on the same page, right? So Colab, Google Colab. This is a free service Google offers. There are premium options available, but this is a free service. And I personally use it for a lot of my classes. For some of my classes that I have true big data, Colab doesn't cut it. So I use Google Cloud, which is a separate topic. The Colab itself is sitting on Google Cloud. However, you don't have to have a Google Cloud account to use it. And it's just excess capacity. You just need to have a Google account. Doesn't have to be a Google Cloud account. But with bigger projects, you are going to need some sort of funding, which also I apply on behalf of my students. I get them funding for those courses. For everything we've done with DSECOP, all these physics modules, which we'll talk about in a second, you do not need big compute power, and Colab is powerful enough to run. Now, if people are new to Colab, let me just bring up an example, and the white background would be a little bit better. So this is it's a sample environment that, make sure I'm zoomed in, that, when you come in, you would get something like that. The notebook that is running here is a .ipynb. It stands for Interactive Python Notebook. So that's the Jupyter notebook, basically. So Colab is running a Jupyter notebook. Is in fact using the Jupyter open source, and they have added some layers, beautified it, and put this piece of software on a Linux machine, sitting somewhere in the one of Google's data centers. And before you run it, this just looks like a Google Doc. It has some text, it has some Python code, it has the output of the code, and uh, yeah, so you can also include HTML and other things here. So you can have multimedia, you can have the output of the graph, images, videos, all sorts of things. Okay, so right now this is just working very similar to a Google Doc. But when you connect, then you connect to a kernel. The kernel is compute hardware sitting on Google servers, and now I have access to over 12 gigabytes of memory and 100 gigabytes of disk, right? I can now run the code here, not using my CPU of my laptop, or memory of my laptop, but everything is being run on this machine. And again, I would distribute the slides, so you can go here. But this is the notebook I'm sharing here is shared by Google. This is a sample notebook. You can also just search for it, but there will be a link in the slides here. So now you have it. This is a piece of Python code, is equal to 10, and it's going to print A. You run, and it works, right? Pretty straightforward. And here you have markdown text, which one can edit, right? I give all of my lecture notes in this fashion, and my students can even modify, can add things to it when they're taking notes during the class. Okay, so we did the same thing with the DSC Cup project and use Colab. Yeah, so let me move on. I want to just mention a couple other projects that you could potentially consider for your own courses if you didn't want to use Colab. One is mybinder.org that allows you to set up this virtual environment for your students and with everything pre-installed. The other one would be our Studio Cloud. If you, for some reason that we should discuss maybe after this call, if you want to use R, then this would be a good solution for that. But I would not advise going towards that route, because I say everyone means 80+%, not 100%, using Python for data science projects. Okay, so being in the cloud allows you to customize the machines and set the get a machine for the exact needs that you have. I should also point out that nothing in the cloud in cloud environment is free. Of course, when you're in the educational institution, at least for now, and this has been the case for the past decade, Google supports and offers these educational fundings for either you're taking a course or for research. You can get credit to run, but these could be like who's paying for the compute for the cloud. That could be an issue of its own, which is something that can be discussed later. However, this is much more, let's say you're a startup, this is much more doable for a startup to find money to pay for their compute, as opposed to find money to set up a data center, right? That's a big chunk of money that one has to to find. Okay, next, code sharing, GitHub, I mentioned. This is the platform that we chose, which is pretty easy choice for DSE Cup to run and to collaborate for us, to work the code here and have the code review and everything, but also to share with the community. Okay, now let's talk about DSE Cup, uh, data science, the data science community of practice and data science education community of practice. So this was funded, the Innovation Fund in 2021, started 2022. These 6 PhD students at the time, some of them are professors now or postdocs. They were the first cohort. They started working on this on different modules, which I'm going to point out, and they are public to everyone to use. And this is our second cohort, 2023. Yeah, so six people each year. And on average, each person worked on 2 different modules. So let's talk about the modules. Again, I do have the QR codes here, so feel free to use and go to or this is also a case sensitive short link, so you can also type it in, but I will share the slides so you have access to these later. The These are the modules that were developed by the fellows that USC hired, and maybe this looking at this map be a little bit more intuitive and just to give you a sense of what kind of modules are here. And of course, this is a lot. There's a lot of content here. At the same time, it's not enough because there are like so many other areas that we could potentially um, elevate the concepts and make it easier for the students to understand the physical concept, at the same time expose them to data science techniques if that's part of the goal for your course. But on the left hand side, we have these 4 modules that are designed for, these are like general data science modules, and actually one of them is just a professor's module, that how to get started, how to use these things. Let's say um, I value data science and I want to introduce it in my physics courses, but where do I start? This module is going to help you to get set up with that. But also, I know my students are coming to my course without any sort of programming or data science background. What can I give them, or what kind of content I can give them that is still related to physics, but it's data science and it's introductory. So there are some components here. You could take this module, for instance, and use it for, if your class is 3 hours, or 2 1.5 hour classes. Usually these modules are designed for that duration, that length. But you can also do a mix and match. You can maybe say, okay, I really like the first 2 notebooks. The modules are designed in multiple notebooks. I like the first 2 notebooks of this module and the third one here. You could mix and match, right, based on your own needs. You could take a module and modify. You're not the copyright is very generous, the copyright that we have, and you can take it and modify and make it your own based on your students and your course's needs. Okay, and then on the other side, we have modules that are related to machine learning and some more advanced topics that could fit in uh, specific physics domain. And then we have specific physics or course domains. And then we have the it's like beginner is a solid border, so we have also categorized them that way. And then the intermediate is the dash border, and the advanced is the dotted border. So we also try to separate them in that way. Um, The prerequisites for these modules, what we have assumed that students will have before coming to these modules, has been the following. The core Python, they just understand basics of programming variables, functions, loops, etc. The core functionalities of NumPy, Pandas, and Matplotlib, although we do have these concepts mentioned in some of the introductory modules. But the goal was, hey, there is a lot of content out there in the world, a lot of books, a lot of, some of which I talked about earlier, that is on these stuff. Like we don't want to recreate, we don't want to reinvent the wheel. They're already great, so you can use those. But when it comes to how do I bring in data science into my physics courses, then there's a challenge there because adding a data science course to physics curriculum, physics undergraduate curriculum, that's tough. There's not a lot of room for that. Removing a content, removing a topic, bringing data science to that course, that's also tough, right? There's a battle that we think everything is important, and it is. So it's hard to make that sacrifice. So we are hoping that this solution is that, hey, you can still teach the topic that you want to teach, but let's use some data science. Let's give them an exercise to work on at home. So not only they're learning the physics concepts, but we are reiterating that concept, now solving it in with some data science techniques, right? We're giving them some other skills that they can use them elsewhere too. And then the basics of working with Git and GitHub and elementary stats. So these are most of the assumptions that we're making before getting into these modules. Also, if you wanted to maybe get a better overview of these modules, because I think we have like 20 or 21 of them. We recently published a paper. Some of us wrote this paper on basically the community of practice that we formed and we worked together. So some lessons learned from here, I would suggest to go through this as well. We showcase a couple of the modules there, but I think best would be just go to the GitHub and browse. Okay, I will actually, I think one of my slides. Oh, this is the slide I wanted to jump to. Maybe I want it to be here. So let me go to our GitHub page. And while I'm here, I might as well share the link to the slides just in case someone wanted to follow along. Okay, here's the link to my slides, but you don't have to. You can just watch me. So this is our GitHub page. Each folder here is one of these modules. As I mentioned, approximately each module takes about 3 hours of class time. Some you might be able to finish sooner, less than 3 hours. Some might take a little bit longer. Some, the 3 hours is just the class time, and there's another 3 hours worth of exercises that the students have to work on. So you have to go through, and you are at the end of the day, you are in charge, you are in control, what you want to use, and you can modify. So most of these come with exercises and with even some quiz questions, some of the modules even with slides. So here is the list. I wanted to showcase one of the modules in the time I have, which is the automated object detection. So this is by one of our fellows, Karan Shah. Karan actually was our fellow both years, and he's developed some really good content. This particular module, for instance, can be used in any physics lab. The idea is that, hey, let's collect our own data with the experiment that we are doing with the object detection algorithm that we can run the algorithm. It's all based on open source. The students can go through the code and they don't have to understand every bit of it, but they can. So if a student wants to spend time to understand how this object detection algorithm is working, they can, but they can just take a video in the lab, upload it to their Colab, run it, export a CSV file, and start playing around. They can do all sorts of things and write the lab report, but they have this like sophisticated code that they can improve and they can modify, right? So this is what this module does. It has three different um, three different notebooks. The first one, for instance, is an introduction to image representation and manipulation with NumPy, which I'll open in a second. It's pretty cool. The second one is using the operations discussed in the previous module. So there's another module actually this is building on, but it's showing the how the object tracker algorithm actually works, and they can try it on their own videos. And then yeah, then the, the third one is a little bit more advanced. So let me go to the um, so since we have reached the recording limit, is that an issue? I'm not sure who that comment is. Oh, that's somebody's note taker. I don't even know if that is legal to have someone send their note taker to the to a meeting. Okay, let's um go to one of the notebooks, for instance, images. And so this is where the students would download, or you could download the only module that you need and then put it on your own course site or GitHub or whatever platform you're using. But this is where faculty will come and see. For instance, this is the first notebook. You could also open it directly from here in Colab. So we are already familiar with Colab. Point we can go through this and um, go ahead and maybe I switch my background color again to bright connect. So it would be able to run this particular notebook. So we don't need to run everything. We can also just go ahead and view the output notebook, and that's what I'm going to be doing. But just to give you an idea, this notebook starts with talking about what images are, right? They're nothing but some numbers, right? Each pixel is a number or multiple, depending on how many colors and etc. you have. But it's going to allow the students to just play with NumPy arrays, understand both images and NumPy arrays, and do some basic operations. And yeah, so it's a pretty cool exercise. So they can try to replicate some of this on their own. But then, just like a grayscaling versus colors talks about that. And also, yeah, here's a colored image. Then starting to play around with these numbers, right? What can we do? It can easily zoom in, you can rotate, you can apply some transformations on these pixels. And so this is a very interactive way of allowing students to learn. And this part is mostly about uh, data science and images, right? Computer vision, less of physics, but the application can be applied to physics problems, which we were talking about in the physics lab, for instance, right? So this goes through, and some of the content for this particularly this notebook maybe can be given to students as a pre-work. Let's say you read this, and then you come to the class. We are going to start with the notebook number 2 or notebook number 3, and so on. Okay, so um, and yeah, so let me Let me see. No, one more thing I wanted to talk about, and I'll stop and see if there are questions, discussion on this, which is where is the where is AI, speaking of AI note taker, where is AI now, and how can it help with education, especially education in data science? I just put a placeholder slide here. Um, just this is not the focus of this talk, but I think it's very relevant, and we cannot deny the existence, right? This is the big elephant in the room, which is that the AI tools that are out there have become really good at coding, at doing quote unquote data science to a certain point. Now, if the students are not able to use them, they wouldn't be efficient. They wouldn't be efficient enough to operate the project. Also, I've seen a lot of students that are able to use them just barely to be able to copy paste and not understanding where the hallucination and the errors are happening and to be able to catch that, which is also dangerous. But my personal fear is the fact that students can get away using it and come to your course, get a good grade, and move on with their lives without, or a lot of courses, or maybe to get a whole degree without truly understanding the concepts that we want them to understand, and be able to do problem solving on their own. So I've thought about this, like all of us, like the rest of people on this call, in the past few years, how to battle. One of the things I have done is to reduce the amount of weight on anything you give them to work on at home, the homework, projects, anything to do at home, because then it could potentially be grading their subscription plan. Do they have a $200 a month subscription or a free subscription? And if both groups are using it, um, then the one with a more advanced model is giving better response, and you're giving them higher grade. Or if somebody's not using it, then it's unfair to them. So I give a lot of the grade is based on presentations when they come present, answer questions. The quizzes I have, they're on paper now. They used to be on they used to be on the um, open internet, not anymore. I see there's a comment that some universities have subscriptions. That is true, but I doubt if they have a $200 a month subscription. So there's always going to be a more expensive model that not everyone has access to, and that could potentially be an issue. It is good that some universities are doing it. Uh, I haven't seen that happening to my university yet. So anyhow, uh, what can we ask the students to do? We can ask them to use it in a proper way. Um, the way I ask my students to do is any questions you have about homework, or in general, you can guide the AI with a prompt engineering technique. Say, act as a TA. You're my TA. Help me solve this problem. You have a TA at your disposal. Don't give the problem to it to solve it for you. Then you're not really understanding how it was done. But you can act as TA, or debugging code and commenting code, improving readability, efficiency of the code, understanding. Let's say, just showed you this notebook. The student can easily copy paste the content, say, explain different parts of the code, what is happening, or explain this particular part. Can be very, very powerful, and help with education and their educational journey and experience, right? Help me prepare for the quiz, generate some quiz questions, copy paste this whole notebook, right? Just very easy for the students to copy. Let's say, come here, copy the entire content of this notebook and paste it to the Gen AI tool as a prompt. So generate some quiz questions for me. Could be helpful for us too. right? Make this question I have more difficult or more challenging or a little bit easier. But yeah, for my main thing is for the students. How can we help them to use these tools more um, efficiently and effectively in a way that they're not sacrificing their critical thinking? They're still in the driver's seat. They understand what is going on. They can catch the AI tool when it's hallucinating, it's giving the um, nonsensical answer, as opposed to just copy pasting things that they're seeing from there. Okay, so I am at the end of my slides. I'm going to stop right here. Thanks and thanking everyone for giving me your time. We have 12, 13 minutes left. So if there are any questions or any topics, and this is a small enough group, right, Patricia? We can ask people to speak up. Don't have to necessarily use the chat. So I see you're nodding. I'm not hearing. I can't hear you. I can't hear you, Patricia. I don't know if it's anyone else. Can other people hear Patricia?
I do not.
Yeah. Hi, William.
Hi, Mohammed. Patricia, it could be your microphone or the setting of the audio source or something.
Okay, while we're waiting for Patricia's mic, are there any questions? And I should say, kudos to William Radcliffe, who's here, Alexis Knopp, who's also here, and two other of the DSE Cup leaders who are actively involved with this project, especially with the funding at the beginning. And, in addition to all of the fellows that I mentioned their names. Okay, so Patricia is putting in the chat that feel free to unmute and ask questions if you have any questions.
I'll ask a question. What's the most common problem you see with students starting out with data science stuff?
Hmm. Most common problem, most common challenge.
Yep.
I think the most recent issue I'm seeing, with the AI, ChatGPT, is the code quality is gone to the roof, right? All the code, most of the code they're submitting is well commented and but oddly similar. That's where I started to use some techniques to because that's just some students, they don't see it as cheating or unethical. They are using the tool. It's just a tool, right? I'm using a calculator. You didn't say I can't use a calculator. Or even if you did, I want to use it because this is faster. But I think that's the biggest challenge, especially for the beginners, to to really sit down, struggle, debug, go read, 20 Stack Overflow pages until you find out what the issue is. They are not willing to spend that kind of time. So to me, if you're not able to think in a logical terms and understand how to break down this problem into smaller pieces to solve, then that's a big problem. See, Patricia's question, how do you negotiate with physics colleagues, the curriculum of the data science course? Actually, maybe that's the question for everyone, because that's the challenge, right? A lot of a lot of cases, the curriculum is set. You're not the only one that can control what goes. And if I understand correctly, that what is the um, data science component we can bring into these courses, or can we add a data science for physicists course, which is even harder to ask because that's a whole brand new course. You have to go to the university and get approvals for that, right? Anyone wants to share their experience on this?
Well, maybe one thing I'll interject with part of the design philosophy of DesiCop was that with this module system, you don't have to, right? If you're interested in bringing data science into a course you teach, you could adopt one of our modules. That's a choice that you could do on your own, provided that there's a free slot in the class. And you could do this and see, okay, well, how does this go? Or if a coworker says, "Oh, okay, I'm interested in putting some data science in my class," then you might go and say, "Oh, you're teaching stat mech. Well, here's a module that you might be able to use and adapt and put into your course." And if there is this sort of grassroots effort, then you could come together and work on a course. And while we give you some sequences that might be useful, this is more sort of the integration throughout the curriculum approach as compared to the I'm going to have this one glorious professor and she's going to teach data science for physicists and come and develop this with all the free time that she has.
Exactly. And here's again back to the list of the modules that we have that can be incorporated into some of the existing physics courses and content. And um, in some cases, one module could become a project for a course or a big assignment, right? That they can read and answer. Um, so that's this project, as William mentioned, I mentioned earlier, is a response to the challenge that Patricia is raising, which is the difficulty convincing everyone that this is what we want. But it's not just convincing them; it's the reality that okay, like, how can you graduate with a physics undergrad degree without, um, I don't know, knowing Schrodinger's equation, for instance, right? So can't just say, okay, let's just drop that and add some playing with histograms, or it's not going to work. But you can combine them together and modernize the education. Also helps the students to grasp the content, the material better. Yes. So the collabs, the notebooks we have, they often include assessments, and so most of them are in a form of assignments. And the assignment is as one of the notebooks, and the answers are not there. Now, if you are the faculty teaching it and you want to use the assignment, you get the assignment. You can reach out to us. You can either email me, or you have another email address for faculty members, and we will share the answers, the key with you.
There, speaking of using assignments, how do you deal with the machinery of getting feedback to students and linking up with the learning management system and things like that? Like I know NB Grader exists, but that probably doesn't work well with Colab. Right now I'm using CoCalc, which it works, but it's not great. But managing any reasonable number of students always seems to be a pain, passing notebooks around back and forth. So do you have any suggestions on that plumbing of actually running a class?
Actually, I should say the NB grader you mentioned, that was my experience last time until I gave up on this whole idea. I'm gonna have to try the other one. If you don't mind repeating the name, was it NB Calc?
I CoCalc is like another cloud
CoCalc.
computing service,
CoCalc,
but they
okay.
they have a like classroom feature that tries to mimic some things that NB Grader does, but it lets you push assignments out to students, collect them back, add feedback, and then push back the thing with feedback.
Hmm.
But then it doesn't really link up with your LMS, so I just copy over some grades. It's not my
Yeah.
favorite. Nothing vanilla NB Grader is better, but I'm not paying to run a Jupyter Hub server. It's a big pain. So I haven't
Yes.
found anything that works great, at
And can I
least.
ask, are you using it for a computational physics course or for more of a data science based course?
It's called computational physics, but it's really introduction to programming in Python with a few physics examples.
Okay.
So at the very end, we do some curve fitting and integration and differential equations, but most of it is, here are numbers, here's strings, here's loops, things like that.
Yeah. So the reason I'm bringing this up is that I feel like for some of the physics, computational physics courses or CS courses in general, it's much more straightforward to have these cases and automate grading. But for a lot of data science problems that isn't unstructured, it's I always find it challenging, and there's a lot of manual process involved. And I personally have utilized good TAs over the years. I've learned how to hire better and better TAs, and how to train them to help me with this. Because if you're teaching a class of 60 and they're each submitting a 20-page notebook, that's you need quite um, um, manpower to go through it, and it's hard to automate it. Thank you for sharing that. I will look into it to see how this part of it, if it's automated and standardized, that would be helpful.
Do you have a sound?
Oh, Patricia, I could hear you. Can you say it again?
Oh, I was just testing if my sound works.
Yes, yes.
Okay, okay, that's fine. I didn't do anything. I wonder if anybody else has any other questions. We are getting close to the hour, and I want to be respectful of everybody's time and energy. I do have another question. Um, So, maybe this is related to the message that Alexis put in the chat, which is how a course like this one would look like for physics freshmen.
For freshmen.
Yeah, because I think this is such a useful tool that if we expose to our students and at a very early stage in their training, they can really maximize the usefulness of the tool.
Yes, I think in an ideal scenario, you would have a physics department that different faculty members are talking about what we want to put into, let's say, in terms of like the computation and data science. What are we putting in our curriculum throughout? And some of the content that we have here certainly could be used for freshmen. For instance, we have a module on introduction to histograms, right? That can be used anywhere. And that is, there's no, except programming, some programming is assumed here, which also, again, can be given to students as pre-work. But besides that, you can just get started. And histograms distributions, it is used everywhere in physics, right? So once they learn how to do this in Python, they can just use Python, and instead of some other tools they might be using, just to encourage them to use these scientific libraries and these open source libraries in Python. So that's what I would say. Like some of these modules that can be used throughout, can be used in the labs, can be used for different courses to be put in freshmen. And some of the modules are tied down to um, E&M course or a quantum mechanics course, but some of them are very introductory and can go into a lot of different courses. But you don't want to repeat them. And you want to also kind of know where this concept was taught previous semester, last year, so you can build on top of that.
No, I see. I
And
see the. Mhm.
So I just wanted to add one more thing that the other thing that this map is showing is the sequence of these
Mhm.
modules, that the prerequisite for it. So if you are going with this module 235, you kind of have to assume the students know the concepts here. This is pretty advanced, right? And hopefully, our hope is this is helping that kind of planning, that kind of thinking, where in the curriculum we're adding these modules. By no means this is a full list, right? We would love to continue this project and add more, but this is the starting point that you don't have to have a faculty member building all of this content from scratch.
Okay, well, we are 2 minutes after the hour. Thank you so much, Mohammed, for this very useful presentation. And I'm a strong believer of developing these tools and to support our students. If no one has any other questions, I'll probably say thank you. I see comments on the chat. Thank you for joining today. And I hope to see everyone at the APS Global Summit, right? Okay.
Thank you, and thank you for having me.
Okay, thank you, Mohammed.
Bye bye.
I'm going to stop the recording.